Okay, so let's get started. Let's do a quick recap of what we did in the last class. I think, yeah. Okay. So in the last class, we started looking at what is called convex functions. In particular, we looked at a specific case of convex. So we defined what a convex function is, right? So essentially, you take 2 points, look at the height. Let's say a function value at those 2 points, join the line. That line lies above the function, right? That's the definition of your convex function. So the consequence of that is, if you look at the Hessian, which is the second derivative, that's positive semi-definite, right? So it turns out that it's an if and only if condition. If the function is convex, then the Hessian will be positive semi-definite. If the Hessian is positive semi-definite, then the function is convex. We saw a few examples. Norm is convex, and then we looked at other examples also. Then we looked at another way of checking whether a function is convex or not. The first way is what? First principle, right? Go by definition. What is the second way? Second derivative, Hessian, prove that it's positive semi-definite. What is the third way? So you just pass a line through 2 points, x and y, which is x plus ty, and then look at that as a function of t. T is just one dimension, right? If you can prove that g of t is convex for all t, then the function f is also convex, right? So we saw that in the last class, and we used that to prove something. There is a small issue here. Can somebody, did you get a chance to look at this and figure out what the issue is with this? What is the issue? Any issue in this? The proof of this? No? Well, what did we assume? Well, x and y are positive, semi-definite, symmetric, all that is great. What is the other thing that we assumed? We assumed that this I plus x inverse y, right, has an eigenvalue decomposition, which is u sigma, u lambda, u Hermitian, right, which need not be true in general, right? So it works only if identity plus x whole inverse y is eigenvalue decomposable using unitary transformation, that is u lambda, u Hermitian, right? That was a gap, so which we will fix in today's class. And then we looked at a few more examples, and then finally we started looking at the unconstrained optimization problem, for which we proposed an algorithm called gradient descent, which is very easy. So you take a point, some initial point, look at the gradient direction, you move in the direction of the gradient, right? So that's what, or rather, you move in the direction of the gradient, right? So it's a simple algorithm. The way you update xt plus 1 is through this equation, right? So let me call this as GD. Okay? So whenever I say GD, this is the equation that I'm going to refer to, right? And then finally you do it for capital T rounds and return x capital T plus 1, right? That's what you return. We started analyzing this gradient descent algorithm, so which we will continue to do today as well. So first of all, we made a specific assumption here. The assumption is the Hessian is not only positive semi-definite, it's greater than or equal to some lambda times identity. So what do you mean by that? You look at the difference, right? The Hessian minus lambda times identity. That matrix is positive semi-definite. Okay. So if you assume that, this is called the strong convexity assumption. Okay. So this particular assumption is called strong convexity. I'll just write it here. So we say that the function is strongly convex if there is a lambda greater than 0 such that the Hessian is greater than or equal to lambda times identity. Then we say that the function is strongly convex. It's not only convex, it's strongly convex. So why is it called strongly convex? So if this is not true, what do you mean by, what is the condition? The condition is, of course, f is convex, right? That means Hessian should be positive semi-definite. That means for certain values of x, Hessian could be 0, right? You agree? Here 0 meaning, when you look at x transpose Hessian x, that will be 0. That means in some direction when you project, you'll get both will be orthogonal, right? So it will be 0, right? So when can that happen? That can happen when you have linear terms, right? For example, a bucket kind of a function, right? If you look at the bucket sort of function, the domain of the function where the function flattens, right? For those values of x, the Hessian will have, yeah, it will be greater than or equal to 0, right? So it won't be strictly greater than 0, right? So in which case it's convex, but it's not strictly, meaning it doesn't have a pointed shape like this, right? Do you agree? Because you take 2 points, if you join the two bottom line here, let's say if you have like this, if you join these two lines, these 2 points, then the function doesn't lie below it. It lies exactly, it overlaps, right? That's why it's called convex, but the other one is called strongly convex when it lies strictly below. Okay, so now what is the consequence of this? So let's look at the gradient descent itself. Let's see what happens when you move one step from xt. So this is your xt and this is your xt plus 1. You have moved one step. I can write this as f of xt plus, how did you get this first equation here, this equation? How did you get this? Can somebody tell me what was the rationale behind writing this? What is this called? Remainder form of Taylor series, right? That's what we did. Then we said, well, if you look at the Hessian is greater than or equal to lambda times identity. So we could replace, I can think of xt plus 1 minus xt as x. So it's like x transpose Hessian x, right? Definitely that's greater than or equal to lambda times identity. So I just replace it by the same, right? We got lambda by 2 xt plus 1 minus xt transpose xt plus 1 minus xt. So it's like x transpose x, which is the inner product, which gives me the norm squared. So we got the norm squared, right? Then we invoke the GD step, right? So xt plus 1 minus xt is nothing but negative of the gradient, eta times gradient, right? So I just substituted gradient here. Gradient transpose gradient is again norm squared of the gradient. Remember, gradient is a vector, right? And you have lambda eta squared by 2, this. So essentially what we ended up getting was this equation here, right? So let me write this equation. So let's start. So what do we have? So proof of convergence. This is a very general proof. Okay, so even if you look at today's paper, right, let's say today's meaning, if you go to NeurIPS or ICML, whatever conferences, and look at the papers, the moment you see some of the proofs, you will recognize it's exactly similar to what we are trying to do. Okay, so there is a similar sequence of steps. So let's see, we got this, right? F of xt plus 1 is what? Is greater than or equal to f of xt, minus eta times 1 minus, what do we have? Lambda eta by 2, norm of gradient of f xt whole square, right? Do you agree with this? Okay, so now see, the function is like this, right? So this is your function and this point is the minima. Let me call this point as x star and the corresponding height as, I'll call this as p star, which is f of x star. This is the bottom, this is the minima. That's where we are heading towards, right? We want to get to x star. So now if you look at any xt, right, so xt will be somewhere here or here, anywhere, right? If you look at the corresponding value of the function, it's larger. Do you agree? So f of xt is definitely greater than p star. You agree? So if I replace f of xt by p star, I'll get a lower bound, right? Greater than or equal to minus eta times 1 minus lambda eta divided by 2 gradient of f of xt norm square. Okay, is that fine? Okay. So now what is it that we are saying? So let's look at this. F of xt plus 1